So I'm going to do something a little bit different. I've been working in AI for about 20 years or so, AI and design, so a long track record. But this is the year that it's had the most sort of public show. There's been a lot of talk. So instead of showing one project, I wanted to use a bunch of projects, several of them, show them very briefly to try and articulate something of where we are and where we should be going. I can use this, right? Now, there is a similarity between AI and BIM, because I think in general, both of them, we tend to aim for better and more reliable models. So the single source of truth we hear quite a lot. We want to reduce the error in those models, but potentially there are other ways of dealing with things. And I want to make a sort of design case that tends toward decentralization. And some of the, I won't mention blockchain in particular, but some of the things that go along with that. This is probably familiar to most, the so-called McLeany curve. This is by Paulson back in 1976, I think the first articulation. And what it shows, of course, is that as you move along the timeline in design, you've got decreasing influence of your changes, but the costs increase. So the idea behind BIM tends to be that we want to shift all of the effort toward those earlier stages where they're cheaper and can have more effect. But there's a bit of an irony here, because this is the most uncertain part. This curve downwards is also roughly representative of the amount of uncertainty in a project. So we have the most uncertainty at this point. We have the least knowledge of what's going on. And we can use AI to manage that uncertainty. And now in my experience, I'll just show you a few examples. We have used AI to manage uncertainty all the way along, right from the start to the end of the project. So just very briefly, a few examples. In pre-design, this is some work going back over a decade now. David Hawkins and colleagues were looking at energy performance. So using a fairly simple neural network and data on various design variables, building orientation, amount of glazing, cladding type, and so on, to predict the energy performance of the final building. And they could outperform the standard energy benchmarks of the time by 25 to 40%, it seems. Going on to design. Another example, a lot of simulation that we do in the context of design, a lot of very computationally intense simulation. This is some work principally by Sam Wilkinson looking at computational fluid dynamics, which is very, very complex, takes a long time to get accurate results. But in this case, he trained up a neural network on data from previous CFD outputs to outperform most of the models. So you can predict not the energy performance here, the consequences of wind flow on buildings in the context better and faster than actually running the simulation itself. Going forward on a construction, particularly if that construction is automated, this is one of the more extreme examples here, the carving of wood, heterogeneous material with a chisel. Julia Bernaro's work here, teaching an industrial robot to do what normally takes a lot of handcrafted skill to produce. You can scale this down to much more conventional construction, but this is one of more extreme examples. And you can teach an industrial robot to do this as well, even though it's normally a handcrafted sort of thing. Finally, into management, this sort of thing is much more conventional, I think. But Scott Fang and others looked at using, in facilities management, asset management, looked at both text-based and image-based techniques to automate the asset management process, assessing the quality and the classes of various building assets. And then finally, still at the far end, the operational side of things, if the building itself is automated, this is an example by Gennaro Senatore a few years back, looking at the trusses that are active. They've got actuators in the trusses to change the scale of each of the struts dynamically in response to various loads, so that instead of having more steel in the truss, a thicker truss, a heavier truss, you can actually maintain the same stiffness by the actuators, which you can see turning off and on here. Now, in this case, this is actually beneficial. Even though you pump energy into it to operate them, that energy is less than the overall embodied energy that would be in the extra steel that you'd have to put into these. Now, you can see a bit of a flex here, but the point about this is that this is entirely because of the lag in the system. We don't have the actuators hooked up to an adequate sensing mechanism or the prediction of where the load's going to be in this case. But that becomes a data problem, becomes an AI problem rather than a material problem. So one that's ideally much cheaper to solve. if you've got the right technology. Now, the thing about all of these, though, is that even though they run right through, they reduce uncertainty right through the process, is that the kind of uncertainty they're reducing is not maybe what we would call true uncertainty, at least not what John Maynard Keynes called true uncertainty when he wrote this back in 1937. Here he's distinguishing between risk, which is something that you can articulate what the level of uncertainty is because you can quantify the probabilities, and true uncertainty. So he makes a distinction between, say, a game of roulette, because it's probability, and the weather even, only moderately uncertain. But he talks about the real uncertainty, true uncertainty is the prospect, say, of a European war, which is truly uncertain. You have no scientific basis on which to calculate the probabilities of that. We just don't know. So this is a real kind of uncertainty that we often have, particularly toward the beginning, the design phases of a project. Now, in the past 20 years or so, there's been a distinction made, say, between standardized components and parametric variable components in design, or between mass production and mass customization in production. And the division is between the two of these things. And the technology that we have has been based on the latter. But effectively, these equate more or less to the well-known and the simple risk. And there's an even more important division, I think, now between both of those and what Keynes was calling true uncertainty. This is the kind of thing that's very difficult to deal with. Now, Keynes said that we follow about 3 different rules in doing this, or 3 processes. One is to assume the present is a serviceable guide to the future. The other one, we just assume the existing state of opinion expressed in the market in his case, but that is correct. It's based on a correct summing up of what actually is the case. And 3, we fall back on the judgment of others, of people, our peers, the majority or the average. Now, these are the things that we tend to do, we fall back on, but these are also the things that AI and machine learning typically does. It finds a pattern, fits a model to the existing data, and it aims to minimize the error in that model. It aims for a better fit. Now, that works in some cases, but it tends to work in the problems that Rittel and Weber would have called tame problems, as opposed to what they called wicked problems. So I've shown tame problems up here, I've called them optimization problems. These are the kinds of things, maybe very difficult, but I've given the automotive and aerospace industries as examples, because even those are very complex, we know a lot about the definition of the problem, we know a lot about the production method, we know a lot about, because we're often producing many of them, we know a lot about the system that's set up. So we can set it up at the start, we can apply our optimization, we can apply our standard machine learning and so on, and we can solve the problem by a known route. Wicked problems aren't like that. They change all the time, they're unique, they're difficult to quantify and difficult even to specify. So that's the difference. Now, just to give a few examples of where the problems actually are, I took a few examples here from the UK's recent AI white paper. This is the AI strategy for the next few years. And near the beginning of that paper, it lists a few examples of excellent results in AI, test cases that are superb. The first 2, AI helps piece together the first complete image of a black hole. The second one is AI solves a decades-old protein folding puzzle. Now, both of these seem superficially to be very similar. They're both scientific results. They're both taking data together and coming up with a scientific result. But actually, they're very different in terms of the wickedness of the problem, let's say. So in the protein folding case, it's very difficult, extremely difficult. I mean, this is one of the things that DeepMind was set up and worked on for years. But you can set up a protein folding. You can observe it in reality. You can set up laboratory experiments. You can examine it. You can see it happening in the lab. Protein folding, you can do that. With a black hole, you've got something very far away, light years away, actually happened in the past, completely non-repeatable. So there's no actual sufficient test or validation, particularly if we're doing something like reproducing an image in the conventional sense. Now, this work is actually a little bit more nuanced than that, but you can imagine the kind of thing that we're doing when we're producing an image and we're taking that as the ground truth. We just can't trust that. There is no ground truth in this case. We don't have access to it. And this is the kind of thing that we do, particularly in the generative AI that we're seeing now. For generating images, for instance, the test is just that it looks good. There's very little else that we can do to test it because there is no ground truth there. So that's a problem. Another problem is that often we can't tell the difference just by looking at it. So if we're looking at a photo, we don't necessarily know whether it's valid or not. These 2 images here We do a lot of work in spatial analysis. Both of these are images of London. They look very similar, and the streets are all quantified. The red ones have high values, the blue ones have low values, and they correlate very well. But these are two very different analyses of the streets. Both of them correlate, incidentally, with human movement. But the one on the left is a representation of optimal routes. So if you have people optimizing the route, knowing the graph very well, optimizing their routes, this is what you get. On the right, you've got something that's just a bunch of randomly walking agents. No knowledge of the graph whatsoever. But it's very difficult to distinguish between the two of them. I'll skip over the details of the agents. The reason they correlate is because the space itself is what we call intelligibility. It's designed such that those two correlate. And we've got two spaces at the top here, one on the left and one on the right, that look very similar, but the one on the left has that correlation. It is intelligible. The one on the right, the actual polygons are the same as the one on the left, but they're shifted slightly. And it's difficult to see often if you don't know what to look for, but that's a very low intelligibility. That's not a space that we would want. But we can't necessarily see the difference unless we know exactly what to look for. And with AI, it's often the same sort of thing. Often it appears to pass the Turing test, let's say, but how do we know the inferences are valid? Now, to back up to one of those examples I showed you before, with the computational fluid dynamics, for instance, to go into a bit more of the detail, the first model that we came up with used overall parameters of the buildings, and it doesn't predict very well at all. It's not a very good model. In fact, what we had to do was to go to a completely different model, which is a local model of curvature of surfaces. And this works much better, but it's a completely different representation. The only way to do this is to change the representation entirely. You can't get from one to the next. Now, in design, you have what we might call paradigm shifts all the time. They're quite frequent. A paradigm shift doesn't necessarily have to be something, I mean, Kuhn's definition, it would be something that happens, say, once in a generation, but the same kind of thing happens quite frequently in design. This is an example of some work I did for Anthony Gormley years ago. It's a very complex sculpture of the space around a body. You can just about see the arms and legs there. But to place all of these thousands of individual members, we had to come up with the precise algorithm to place them in space. And the first thought for the model was that it's a series of surface normals. It was obviously, most people would guess that. Most people do when I ask my students. But in fact, that doesn't work. There are all sorts of geometrical problems that brings along if you try to implement it. Actually, what does work is a completely different model, which is a Voronoi diagram of those rods enclosing the space of the cells that emanate from the points on the surface of the body. Totally different, looks very similar, but it's a totally different algorithm. And the way this works in the design process is that we have these various models, these various abstractions that we make by going back and forth, working from instances in the real world, and then conceptualizing what they are and making models of them, and then going back and forth like this. Now, you can't get from surface normals to a Voronoi diagram. That's essentially a creative leap, but you cannot translate from one to the next. You have to remake the model entirely. And this thing happens, I mean, this is an abstract, very simple process, very simple project, I mean, but this happens all the time in design. So we've got these three problems, effectively. We've got no sufficient test or validation, can't always see the pattern, and we've got these paradigm shifts happening in especially early stage design. And if we use AI in the sense in which it often is, by having a better model, more data, and tuning that model, they don't help. They're all solved by changing to a different model entirely. Now, we can do this in BIM. The best example in my own experience is Speckle, software created by Dimitri Stefanescu on our InnoChain project. But the idea of having a centralized model, the standard sort of BIM approach, where you have a centralized model or a centralized standard, and everyone uses that and you agree up front, he was coming up with a replacement of that because a lot of people working in actual design don't have that upfront task. They don't necessarily know what they need, and they need to work with irreconcilable models at different points on this much more distributed chain. So Speckle is effectively a means to transfer data from one model to the next without actually reconciling them. You can create these ad hoc. Now, this, of course, is a network. It's got no central hub. It's a much more complicated arrangement, and we need mechanisms for building trust in our data, for tracing, for responsibility, and so on. But if this is useful in early stage design especially, then this is the kind of area where we have to put more research. This is the kind of area that machine learning is ideally suited for, that blockchain is ideally suited for. Excellent for that. My minute's come up, and it's just about the end, so I'll just leave it with that. I think that if we do that, I think that's one area where research has to go. we're going in that direction, and I think much more can be done. But it may be a case in which we start off, or we have certain types of projects in which we acknowledge there are multiple models, particularly toward the beginning, in those early phases of uncertainty. And the task is to negotiate and to manage those uncertainties and to be able to communicate between those models, a decentralized approach. And then as the project goes on, as certainties bed down, we move to a single model toward the end. Thank you.